I will discuss about electric field. This is a conception by which we can determine what force can be exerted on a charge in space. If Q be the charge and it experiences a force of F in this direction, this is a force F in this direction, this is a vector, then field can be determined by F by Q, or F is equal to E into Q. E is the electric field vector. Now we can define electric field by E is equal to limit Q tends to 0 F divided by Q. Why Q tends to 0? Because this Q is called test charge. And this is a negligible positive charge by which we can define the electric field. If Q be very small, tends to 0, then F also tends to 0. Therefore, this negligible charge cannot change the electric field in the space considerably. So, test charge cannot change the distribution of the field at a point where we want to find the electric field. That is why we always take Q tends to 0. Now, F is equal to 1 by 4 pi epsilon 0 Q into Q by R square and R cap. Now, E is equal to 1 by 4 pi epsilon 0 Q by R square. So, we can say that direction of the electric field and direction of the force acting on a test charge is same. Now, if we consider a very small point charge Q, electric force acting, if we draw a graph to show the electric force around it, then we can say that the force acting on the charge at this point will be like this. If the force vector is radially outward along all possible directions, and so on. If charge remains same at every point, then we can say that force, that is the length of this arrow-headed line, will be same. But consider at this point, length will be shorter than the previous, because force is inversely proportional to the square of the radius, like this. And if you consider this, that will be further smaller than the previous. So, magnitude of the force gradually decreases with the increase of the distance from the point, and it is inversely proportional with the square of the radius, and it is gradually decreases. Now, field lines, that is introduced by Faraday's. Field lines is originated from positive charge. Suppose this is a positive charge Q, and field lines are radially outward from this point. Like this. Advantage of conception of field lines is that if you consider any point at this region, we will observe that field lines are closer at this point. But if we move further away from the charge, field lines are scattered. So we can explain the magnitude of the field by the density of the field lines. More the density of the field lines, more will be the magnitude of the field. Now, if it is a negative charge, suppose this is a negative charge, field lines will enter into the negative. So, arrow will be inward as previous. Now, a positive charge, say 4 unit charge, and another negative charge -1, say. Naturally, 4 unit charge will emit 4 times lines of force than -1 charge, and 4 unit charge will emit the lines of force, and -1 unit of charge absorb that lines of force. We know that emit by the positive charge and enters into the negative charge. You should remember that lines of force always emit or enters into the body normally. Now, the other lines of force are force charge, because 4 unit charge will emit 4 times lines of force, then -1 unit of charge absorb. So, lines of force distribution may be this. And we know that positive charge attracts negative charge as lines of force enter into the negative charge and they contract. Now, if we consider 4th unit charge positive and 1 unit charge positive, what will happen? Lines of force will be outward from positive charge, but these lines of force will be repelled by the 4 unit charge, 1 unit charge, repel each other like this. So, the property of the lines of force is this: no 2 lines of force intersect each other. This is because, suppose this is a lines of force, this is another lines of force intersect each other, then the direction of the force at this point is towards a tangent, and for this, if it is lines of force in this direction, then it will be force at tangential direction. So, we will found 2 different direction of the force or field at a point. But we know that at every point there is unique direction of the field. So, it is not possible to get 2 different direction of the electric field at a certain point. From that we can say that 2 lines of force never intersect each other. So, major characteristics of the lines of force: number 1, 2 lines of force never intersect each other. Number 2, the number of lines of force emit from a positive charge is directly proportional to the magnitude of the charge. So, number of lines of force directly proportional to the magnitude of the charge. Third, it emits from positive charge, that is outward, and enters into the negative charge. This is continuous line from one point to another, but it is not a closed path, because it will be closed path only if positive and negative charge coexist at a single point, but it is not possible. If positive and negative coexist at a single point, then that point becomes neutral. That is why it is not a closed path, but it is continuous path. When it leaves from a positive charge and enters into the negative charge, between that line is continuous. There will be no discontinuity of the line. Now, flux, this is another term, electric flux, that can be defined by number of lines of force. This is a scalar quantity. Lines of force indicates the direction of the field, so it is a vector quantity. But number of lines of force crossing a surface, that is called flux. Now, electric field can be defined is directly proportional to the number of lines of force crossing a very negligible area around that point. Suppose this is a point. If you consider a very small enclosed area, the number of lines of force crossing that area is a measure of the electric field. We can say that, suppose this is a point charge and this is the lines of force. You can compare it with a point source of light from which light is emitting in this way. Now, if you place an area in this direction, then these lines of force crossing this elemented area. Now, we know that if we bend this area, rotate this area, we have to use more area to cover this lines of force, and it is also we can observe in case of light. So, area vector, this is area vector. So, this area and this area are equivalent to block the lines of force. So, we can say that A cos theta, if this angle is theta, then A cos theta is equal to this A dash, and we can measure the electric field as number of lines of force blocked, or we can say that in case of light we can say that blocked, and if in case of lines of force that crosses the line, meaning the same. So E dot ds is equal to phi. That is that. It should be noted that this S is very small, is negligible, because if it is large enough, then field will not be constant at every point. So if we want to get a small an area where field is constant, we have to take small area. So it is E dot ds, that is E ds cos theta, and it is clear that phi, that is flux, is the scalar quantity. Therefore, E can be defined as d phi ds. So, phi can be defined as E cos theta ds over a surface S. This is the flux, electric flux, and this is a scalar quantity. We can define it in this way. Now, we have seen that when there are two opposite charges, in this case, this is positive charge and negative charge. If another test charge is kept at closer to the negative charge, it will be attracted towards this. Suppose this is a positive test charge, it will be attracted towards this. But if we increase the distance, then we will find a point when the force due to the positive charge and force due to the negative charge are equal and opposite, because negative charge will attract this in this direction and positive charge will repel in this direction. So we will get a point where these two forces are equal, and at that point field is zero. This point is called null point. Now, when these are two like charges, whether it may be positive both or negative, a point at the line joining these two charges, we will get a point where field is zero. So, in case of like charges, null point will be between the two charges, and in case of opposite charge, null point will be beyond the line joining these two charges. Now, if we consider two charges, suppose this is positive charge, a 4 unit as stated above, and another negative charge, and if we consider a point long distance compared to the distance between these two, then this will act like a charge of combined charge of 3 unit. And if we calculate neglecting the distance between these two and calculate on the basis of 3 unit charge, then we will get the result. So if the distance is negligible with compared to the distance between the two charges, then resultant charges will be the effective charge for calculating the field or force. But it will be different if two charges are equal. Suppose this is a positive and this is a negative charge, and separated, both have same magnitude CQ and Q, separated at a distance of r. In that case, for a long distance, we will get the field, because according to the previous concept, if we take the combined charge, then combined charge is 0. So according to the previous concept, it should be 0, but it is not so. There should be a field, and this type of setup is called dipole. And dipole is very important, but where in practice we will get the dipole. Suppose we know that if a charge object, suppose this is a charge object, a positive charge, positively charged, come closer to a body which is neutral, what will happen? The atoms inside the nucleus will be slightly, the electrons will be slightly eccentric towards the positive. That is, this will be negative and this will be positive. So we will get partial positive at this end and partial negative at this end, and both have same charge. So this can be compared with this. So we can get dipole from this, and it is clear that in case of calculating the dipole, we should neglect the distance between them in case of atom. But sometimes we can prepare, or we can create a dipole which has considerably greater charge and distance is not negligible. Suppose this is a spherical sphere, two spheres, and these are insulating material, stands are insulating material, and these two spheres are first kept in contact. Now a charged object come closer to it. We know that due to this charge, a negative charge will be induced at this part, and the positive charge will be induced at the farthest point. Now, keeping this object closer, if we separate these two, then this sphere become permanently negative charge, and this sphere become permanently positive charge, and the magnitude of the charge remains same for both the sphere. In this way, we can create a dipole. So it is clear that dipole, when two equal and opposite charge, plus, say plus q, this is plus q and this is minus q, are separated at a distance r from each other, and this line is weightless, rigid, some weightless, rigid body, that is imaginary. Now we have to find the electric field at a different point of this setup. Now first we will calculate for this is equatorial point or broad-on position. This is a bisector, perpendicular bisector of this line, and at a distance d, suppose we are taking distance between two charges by twice l, and r is the distance from the midpoint of these two charges at equatorial plane or broad-on position. Now we have to find the electric field at this point. Now if we join this line, the test charge will be repelled by positive charge. So direction of the electric field will be along this direction, and for this it will be attracted. So direction of the electric field in this direction. Suppose this is E1 and this is E2. As in case of force between two charges, we use superposition theorem, and also we can apply superposition theorem for the field. So resultant field will be the vector sum of these two fields, and it is clear from the figure that this point is equidistant from negative charge and positive charge. Since distance is same, charge is same, so magnitude of the electric field will be same. Therefore, resultant of these two fields will be along the angular bisector of these two. This is the resultant electric field. Now, this line is parallel to this line. If angle is theta, this angle, base angle is theta, then we can say that this is theta, this also theta, and this also theta. So, E is equal to E1 cos theta plus E2 cos theta. E1 is equal to E2, magnitude of field E1 is equal to 1 by 4 pi epsilon 0 Q by D squared. That is distance between these two. If it is, suppose this is A, B, this is C, and this is G. So this is BC square. And we know that BC square is equal to CD square plus DB square. So 1 Q by 4 pi epsilon 0 BC square, that is R square plus L square. Therefore, E is equal to 2Q by 4 pi epsilon 0 R square plus L square cos theta. Now, what is the value of cos theta? This is theta. So, cos theta is equal to base by hypotenuse, that is 2Q divided by 4 pi epsilon 0 R square plus L square L by root over L square plus R square is equal to 2QL divided by 4 pi epsilon 0 R square plus L square whole to the power 3 by 2. So, this is E, magnitude of the electric field at Bourdon position or equatorial position. This 2QL is called dipole moment and it can be expressed by P. So, it can be written as E is equal to P by 4 pi epsilon 0 R square plus L square. Now, if this point is far away from the two charges, then that is R is much greater than L. In that case, we can say that L by R tends to 0. This is far away. So, E is equal to P by 4 pi epsilon 0 R square 1 plus L by R whole square or to the power 3 by 2 is equal to P 4 pi epsilon 0. This becomes 0 and this become R cube. So this is E when electric field, when position of the point is far away from the dipole, then this is very important. E is proportional to, inversely proportional with the R cube. In case of, if we consider a point closer to the dipole, E is inversely proportional to the R square. But if it is far away, it is inversely proportional to the R cube. This is very important. Now, when the points, if we choose another point in axial position, this is twice L and this is the center, that is midway between these two, and minus Q, and this is plus Q. And we are considering a point at a distance R from the center. This is R. Now, this point is at a distance R minus L from the positive charge and at a distance R plus L from the negative. Negative charge will attract that test charge and positive charge will repel the test charge. So, due to positive charge, force will be along this direction. Due to negative charge, force will be along this direction and also the direction of the field. Therefore, resultant field E is equal to Q by 4 pi epsilon 0 R minus L whole square minus Q by 4 pi epsilon 0 R plus L whole square. That is equal to Q by 4 pi epsilon 0 R plus L whole square minus R minus L whole square divided by r square minus l square whole square. That is equal to q by 4 pi epsilon 0. This is 4 RL and this is r square minus l square. This is equal to 2pr divided by 4 pi epsilon 0 r square minus l square whole square. This is E. Again, when r is much greater than L, then E will be 2pr divided by 4 pi epsilon 0 r square 1 minus L by r whole square. That is 2pr by 4 pi epsilon 0 r to the power 4. By cancelling it, we'll get E is equal to 2p by 4 pi epsilon 0 r cube. So, in case of axial position, field is twice the equatorial position. In case of equatorial position, we get p by 4 pi epsilon 0 r cube, and here it is 2p by 4 pi epsilon 0 r cube. Both are inversely proportional to the r cube and all conditions are same. Now, if the point is far away but at some angle, that is, if polar coordinates are given, suppose these are the 2 points, plus q, minus q and plus q, very close compared to the distance, and this is a midpoint, and a point is chosen at r distance and at an angle theta. Now, before derivation, we want to discuss something about the dipole. Dipole P, actually it is a vector quantity. P is a dipole, twice LQ is a vector quantity. And it is obvious that direction of the dipole is along the length of the dipole, that is L is the vector quantity, Q is a scalar quantity. Now, suppose this is at a distance r from the middle point of the dipole. Now, this can be treated as, if we consider a dipole which is perpendicular to this line, we can resolute the dipole moment in two mutually perpendicular direction, one perpendicular to this line and another parallel to this line. So, if we imagine when it is dipole is parallel to this line, suppose this becomes the dipole, and this position is at the axial position, and this is p cos theta. So, in axial position, due to the axial position, its field will be along this, and its magnitude is 2p cos theta divided by 4 pi epsilon 0 r cube. And when it is perpendicular to this, so this is perpendicular, and dipole of this will be, this is q plus q and minus q, and dipole will be field due to this dipole at the equatorial point or Broadband position, that will be in this direction, perpendicular to this, and this will be p sin theta by 4 pi epsilon 0 r cube. Therefore, resultant field at this point is equal to, along this direction, some direction, and it is root over 2p cos theta by 4 pi epsilon 0 r cube whole square plus p sin theta by 4 pi epsilon 0 r cube is equal to 2p, no, we can take p by 4 pi epsilon 0 r cube as common, and it will remain 4 cos square theta plus sin square theta. So, is equal to p by 4 pi epsilon 0 r cube root over 3 cos square theta plus 1. And the direction of the field tan theta is equal to y by x, that is p sin theta by 4 pi epsilon 0 r cube into 4 pi epsilon 0 r cube divided by 2p cos theta is equal to 1 by 2 tan theta with respect to r vector. So this is tan alpha, not theta, and this is tan theta. Okay. Now from that we can get the direction with respect to the reference line, because if it is theta and this is alpha, then total angle will be alpha plus theta, and tan alpha plus theta is equal to tan alpha plus tan theta. We can resolve it in this way. Now torque on dipole due to uniform electric field. Suppose this is a dipole plus q, this is minus q, and this is plus q, and the length twice l. We know that direction of the dipole moment vector p along this from negative to positive. Now if electric field exists in this region, in this direction, we can say that positive charge will be, the force on positive charge will be in this direction, along the direction of the electric field, and for negative charge it will be in this direction, just opposite to the electric field, and it makes an angle theta. This is the direction of the field, and this angle is theta. This angle is theta. Now we know that torque acting on the dipole will be BC into the force due to electric field. Now the force, this force is equal to Q into E in this direction, and this force is Q into E in opposite direction. So the net couple torque, magnitude of the torque is equal to couple of the force is equal to BC into Q into E. BC is equal to twice L sin theta into Q into E. That is equal to twice QL into E into sin theta. Therefore, it is clear that twice QL, twice QL is the dipole moment and E is the vector. Both are vectors. So the vector form of this is equal to E cross P. This is a vector form of the dipole torque due to dipole. Now electric field due to uniformly charged circular arc at the center. Suppose this is an arc which is uniformly charged and it makes theta degree at the center. We have to find the electric field due to this arc at the center. Let lambda be the linear charge density. We are considering a small portion of it. Suppose this makes del theta, and this angle is, say, suppose this is del x and this is x. Now direction of the field will be radially outward in this direction. Now charge of del L length, charge of this elementary length L, del L, del Q is equal to del L into lambda. Del L is equal to R into del X into lambda. Therefore field E is equal to del E is equal to R del X into lambda divided by del Q by 4 pi epsilon 0 into x square, r square. Now we can resolute this in two mutually perpendicular direction, one parallel to the x direction and another perpendicular to x direction. This and this. As it makes here as x degree, so this also x degree. Therefore, if it is E, then it will be E cos theta and E cos x, and this is E sin x. Therefore, del E in vector form will be R del x lambda divided by 4 pi epsilon 0 r square into cos theta cos x in I direction, and this is minus because negative direction of I, and minus r del x lambda sin x divided by 4 pi epsilon 0 r square in j direction. So E is equal to minus integration lambda by 4 pi epsilon 0 r cos x del x 0 to theta minus plus 0 to theta lambda by 4 pi epsilon 0 r sin x del x 0 to theta. This is in I direction and this is in j direction. So this is equal to minus lambda by 4 pi epsilon 0 r sin theta minus sin 0 0 in I direction plus cos theta minus 1 in j direction. Therefore, magnitude of the electric field will be E is equal to lambda by 4 pi epsilon 0 r into root over sin square theta plus cos theta minus 1 whole square is equal to lambda by 4 pi epsilon 0 r sin square theta plus cos square theta plus 1 plus 2 cos theta. This is minus 2 cos theta is equal to lambda by 4 pi epsilon 0 r root over 2 minus 2 cos theta is equal to lambda by 4 pi epsilon 0 r. This is equal to 2 sin square theta by 2, that is 4 sin square theta by 2. So we can write it 2 sin theta by 2. Now considering a ring, circular ring, and we have to find electric field at a distance x from its center along its axis. This is x and radius of this circle is r and charge density is equal to lambda coulomb per meter. Now again we will consider an elementary part of this, and the field due to this elementary part of the circular ring will be along this direction. And we know that if we consider another counterpart of this element, suppose this is theta, if it is theta, and if you resolute this field due to this elementary length in two mutually perpendicular direction along this axis and perpendicular to this axis, and if you consider another symmetric part just radially opposite direction, then this will be in upward direction, so they mutually nullify each other. So as a whole there will be no component along this direction, so only we have this direction of the field along axis of the circle. Now del E, that is electric field due to this elementary charge element, is equal to del Q divided by 4 pi epsilon 0 into r square, capital R square. R, that means this r is equal to r square plus x square root over. So it is equal to del Q by 4 pi epsilon 0 into r square plus x square. E is equal to del E is equal to, and del Q is equal to del Q is equal to del L into lambda. So we can put it del L into lambda divided by 4 pi epsilon 0 r square plus x square. Now the cos component of this elementary of this field due to this elementary length will be del E cos theta is equal to lambda by 4 pi epsilon 0 r square plus x square into cos theta, that is equal to x by r, that is x by r is equal to root over r square plus x square, and del L. By integrating net field E is equal to, if we integrate, all are constant except del L. So by integrating this part, we will get the circumference of the circle, which is equal to 2 pi r. So this is x lambda divided by 4 pi epsilon 0 r square plus x square whole to the power 3 by 2 into 2 pi r. So E is equal to 2 pi lambda x r divided by 4 pi epsilon 0 r square plus x square whole to the power 3 by 2.